Welcome to This Explainer. Today, we're diving straight into a massive, absolutely critical challenge, keeping the lights on when the weather turns extreme. I mean, we all rely on a stable power grid, right? But as we transition to greener energy sources, the very foundation of that grid is fundamentally shifting beneath our feet.
And, as we push globally for carbon neutrality, we hit this really fascinating paradox. We're moving away from fossil fuels to mitigate climate risks, absolutely, but in doing so, we're kind of handing control of our safety-critical power grid directly over to the volatile climate itself. Solar panels need the sun, wind turbines need the wind, so how on earth do we secure a grid when the fuel source is entirely unpredictable?
Well, the answer lies in data. To solve this, researchers have compiled a staggering 10.7 million high-fidelity records to serve as an unprecedented stress test for grid security. And this isn't just a basic dataset. It's a massive, rigorous testing ground to see if our artificial intelligence forecasting models can actually handle the pure chaos of real-world weather. Throughout this explainer, we're going to see exactly why these 10.7 million records for grid security are just so vital.
So, here's our roadmap for today. We'll start with the renewable energy paradox, then look at those 10.7 million records for security. After that, we'll hit the extreme weather threat, explore the AI robustness gap, and finally, look at bridging space and time.
All right, let's jump right into part one, the renewable energy paradox, where climate solutions meet climate vulnerability.
Let's really unpack the core dilemma of modern energy generation. There's a quote from the research that perfectly hits the nail on the head. The energy sources designed to mitigate climate risks are themselves highly sensitive to intensifying weather variability. What that actually means is our grid stability no longer relies on just predicting your average sunny day. It relies entirely on how well we anticipate the unpredictable extremes. If a freak storm rolls in and wind generation suddenly flatlines, grid operators need to know exactly when and by exactly how much, or we risk a total system failure.
Which brings us to our second section, using 10.7 million records for security to build a massive dataset.
Because to build those better predictions, we simply need better data. The R2 Energy Framework essentially uses these 10.7 million records for grid security as an immense, heavy shield. It's designed specifically to test how well AI models predict future weather impacts. The researchers didn't just grab a few days of data and call it a day. They built a standardized, completely leakage-free paradigm that grants 16 different state-of-the-art AI models identical access to future weather signals. It is literally the ultimate stress test to separate the models that are just good on average from the ones that are truly bulletproof under pressure.
And this data, it isn't abstract math. It is forged from 902 real-world wind and solar stations across 4 vastly different Chinese provinces. This geographic spread gives us incredibly diverse meteorological conditions. You've got Anhui with steady, moderate wind speeds. And then you have Shandong, a coastal area representing a highly volatile regime with massive diurnal fluctuations. It ensures those 10.7 million records actually capture the full, wide-ranging wildness of real-world renewable generation. Let's move on to Section 3, the extreme weather threats, and really testing the limits of these systems. Because when we introduce the ultimate physical threat to these stations, things like torrential rainstorms and prolonged heat waves, it completely rewrites the rules. The physics behind why these events are so dangerous are just staggering. In one scenario, you've got extreme seasonal wind shifts that challenge forecasting models to adapt to incredibly rapid, high-amplitude transitions. And in another, massive rainstorms violently drop the solar capacity factor below 0.3. Simply put, thick cloud cover means these panels are suddenly operating at less than a third of their potential. And surprisingly, heat waves often lead to stagnant high-pressure systems, causing literal wind droughts. Extreme weather just flips the physical rules of power generation upside down in an instant.
And because of these sudden shifts, grid operators are basically walking a tightrope out there. They don't just care about some average mathematical error, they care about survival. To measure this, the researchers use something called the qualification rate. This metric tracks the proportion of AI predictions that actually satisfy the strict operational safety margins required for grid dispatch. Basically, it tells us whether an AI forecast can keep the grid balanced and the lights on when a sudden, violent gust of extreme weather hits.
So let's look at how they did in Section 4, the AI robustness gap, or complexity versus reliability.
Okay, so when we take our 10.7 million record stress test and subject our very top forecasting AI to it, how do they actually perform when the weather goes completely haywire? Well, we uncover a massive robustness gap. You might naturally think the most advanced, complex models would win out, right?
Actually, no. The most complex non-autoregressive transformer models completely crumble under the volatile noise of extreme weather. They become highly unstable. Think of them as overthinking the problem. Meanwhile, simpler autoregressive models, specifically ones called GRU, hold the line perfectly. They dynamically process weather changes step by step, adapting on the fly, which proves remarkably stable even in highly volatile wind regimes.
The data really drives this home, proving that a model's reliability under pressure is driven by how well it integrates its meteorological strategy, not simply by cramming in more AI complexity. The simpler dynamic models aren't just more stable, they are computationally cheaper and way more efficient. In the ultra-high-stakes environment of grid security, plain old robustness and stability easily trump architectural complexity every single time.
Which brings us to our final section, bridging space and time for the complete solution.
Look, while AI handles predicting exactly when power is generated, we still have to solve the physical challenge of moving it. Energy resources are geographically uneven. Energy-rich regions are often located really far away from densely populated cities with super high demand. To solve this, we rely on physical infrastructure. Ultra-high voltage, or UHV lines, physically bridge this spatial gap. Traditional power lines suffer massive cost and power losses over long distances, but UHV technology allows us to take that safely predicted renewable energy from our AI models and efficiently transport it across thousands of kilometers directly to where it's needed most.
And the numbers here are just fantastic for the environment. By efficiently importing this clean AI forecasted energy across those UHV lines, these high-demand importing areas saw a massive 10.2% drop in polluting thermal power generation and a 12.9% drop in total local power production. The UHV system actively reduces power sector pollution by shifting the burden away from fossil fuels in those high-demand areas. It proves that securing the grid literally secures our environment too.
So we've seen today how combining spatial transmission lines with a rigorous 10.7 million record for grid security stress test really locks things down. We've learned that simpler, strategic AI outsmarts overly complex models when chaos inevitably strikes. But as we continue to hand the keys of our energy infrastructure over to a highly volatile sky, it leaves us asking one final, absolutely critical question. As the weather gets even more extreme in the decades to come, will our AI keep up, or will the climate always be one step ahead?